welcome to this meeting. As you can all see, we're still working out the technology here. Today, we've got as our guests, Michaela VK3 FUR, Wave, and Mark VK5 QI. Where's he? Oh, he's camera shy, but he's here. So Michaela and Mark are the main developers of Sondehub, which aggregates telemetry from community-run Radiosonde receiver stations. So Radiosonde and balloon tracking and chasing is what Sonderhub does. Has the backend data for. I will let Michaela and Mark talk about that in a second. The club will be open tomorrow. I'll be opening up tomorrow. And apart from that, I don't have any other notes. I'll just hand it over to Mark and or Michaela. Who's going first?
Yeah, I'll screen share. Let me set that up now.
Just something to note here, Michaela's out camping in the middle of Queensland and they have a second screen set up attached to their laptop. That's dedication.
I was expecting to do this from Melbourne or Adelaide, but that did not happen because I had to travel, unfortunately. So it doesn't really matter where I'm doing it from. So I'm doing it from Byfield National Park. And it is raining at the moment, so you might hear little drops on the essentially tent that we have set up here. So let me get this all set up. Hopefully you can see that. Can you see that? I'm assuming people can see that.
Working fine. Excellent.
All right, cool. All right, so yeah, let's kick things off then. I'm Michaela, VK3 FUR. The email address is up on the screen there if you want to contact me. Today we'll also have Mark, who was just chatting before, VK5QI, also has the email up there. And so basically we're going to give sort of an overview of what a radiosonde is, why they're interesting, how to track them, that sort of thing. So I'm the developer of Sondehub, which, as Luke mentioned, sort of aggregates data. We'll get into that in a sec. And Mark is the primary developer of Radiosonde Auto RX, which basically helps detect radiosondes, grab that data, and feeds it into Sondehub. So that's sort of how those two fit together. So yeah, basically a primer on radiosondes and sort of how weather works or weather forecasting works. The Vaisala RS41, which is the primary radiosonde that you'll see in Melbourne. The Sondehub project, receiving telemetry, chasing radiosondes. If you have a radiosonde or you found a radiosonde, how to recycle it. And a new little feature of Sonderhub, which is Sonderhub Amateur, that we'll have a look at. So I'm going to throw over to Mark to give a bit of a demo on Null School's Earth weather model thingy.
Okay, so what you're seeing on the screen is a really cool website, earth.nullschool.net. This is a visualization of the global forecast system weather model. This is a weather model which is run by the US National Oceanographic Administration. And it aggregates data from all sorts of sources to produce predictive models. So this is what the model thinks is happening now. It may not be precisely what is happening now, but it's what the model thinks anyway. In particular, what we're viewing is wind. So the lines we're seeing show the direction of wind, of air mass flow, and the color and actually the speed of the lines as well indicates the speed of the wind. And I can also click and actually show the particular value at that point. Now, what's interesting about this model is that, well, it takes data from huge amounts of different sources. So every ground weather station, There are vertical wind profiler radars, and of course, weather balloons and radiosondes. Now, just as a demonstration of this model, I'm going to look at different altitudes. So we're still looking at wind, and meteorologists like to, so they don't actually use altitude, they use pressure. And this is because the Earth's atmosphere isn't evenly distributed around the Earth. The density will vary with location, and so they seem to use pressure levels. So if we go up in altitude, this is currently viewing ground level, we will find that wind conditions change. So they go higher and higher, lower in pressure, so lower pressure, higher altitude. Things can change quite drastically. At 250 HPA of pressure, we're now at, there's my cheat sheet, 10 kilometers altitude. Wind speed is now wind speed is much higher and in a very different direction. And what you're seeing on the screen there is what many people refer to as the jet stream. Areas of high, very, very high wind speed, in fact, 220 k's an hour. As we go higher still, it's downloading, we end up 10 HPA is about 25 kilometers altitude. So this just gives you an idea of what we're going to talk about feeds into. These models are used worldwide, and this is a US model, but it is used worldwide for predictive forecasts. Australia does have its own weather model. The Bureau of Meteorology has their own models, but they still use these kind of models as well.
So what is a radiosonde and weather balloon and all of that? So what we have is the weather balloon itself, sort of a latex balloon, typically filled with hydrogen. That's the explodey one. Then below that, you typically find a parachute, or in Melbourne, a radar reflector in our case. We'll show you some of those a little bit later. And then there's a big long string, and the radiosonde sits below that. So there's all sorts of interesting things that the radiosonde is trying to do. It's trying to measure temperature and humidity, sometimes pressure. And basically it's trying to look to build that model that Mark showed you. What we're trying to receive is the wind speed and the direction, and that's gathered using the GPS data. So we can infer the wind speed and direction based off the GPS signal that comes back. Sometimes they launch ozone sondes to measure the ozone levels at different altitudes. Being in Melbourne, you are very, very lucky that you get one of the very few sites that launch ozone sondes, and we'll get into why that's very lucky in a bit. But typically the radio signal is around 400 to 406 megahertz, and Mark's lovely software basically scans at nice range to find those signals for us. So yeah, there's essentially sites all around Australia. We'll put up a little map later on. And these are one-time use devices. So typically, with the exception of the ozone sondes, the Bureau of Meteorology do not want these devices back. The instructions on it say basically destroy, well, not destroy, dispose of in a rubbish bin. So yeah, they don't want these devices back, which means we get to keep them and repurpose them and do whatever we want with them. So I'll hand over to Mark for a little bit more in-depth detail of the RS41.
Right, so there's just quite a wide variety of different devices around the world from different companies which perform this radiosonde function. They all do basically the same thing. They'll have some kind of position determining mechanism, so GPS nowadays, and back in the day it used to be radar tracking, and they'll have sensors, temperature and humidity, as Michaela mentioned. The most common one in terms of the number of sondes launched per year at the moment is the Vaisala, which is a Finnish company, RS41. This is an evolution of a range of radiosondes made by Vaisala over the years. And Australia started switching to these about, I reckon it was about 7 or 8 years ago. Now, the nice thing about this radiosonde compared to Vaisala's previous offerings is that it uses lots of commodity parts. Next slide. So a bit of a teardown. So this is the inside of a Vaisala RS41. First up, we have a STM32 microcontroller. Very, well, it used to be very common. They're a little bit hard to get hold of nowadays. Device. Next up, we have a u-blox 6 GPS receiver. u-blox being a fairly large manufacturer of GPS receivers. 6 is quite an old model. That was the current model when the RS41 was first designed, and they're still using them. Next up, we have a radio transmitter, the Silicon Laboratories SI4032. This can do frequency shift keying, and that's it. Again, quite an old device, also obsolete, but Vaisala has large stocks of these, presumably. Then we have the interesting sensors. So we have a temperature sensor, which consists of a platinum wire resistor, which you can just see in the micrograph at the top of the slide there. And then we have a humidity sensor, which is itself a very complex beast of a device. It actually consists of 3 sensors in one package. On the right-hand side is a little, sorry, I should clarify this. Right-hand side is a temperature sensor, yet another one, to measure the temperature specifically of the humidity package. There is a heater, which is on the bottom left. It's very hard to, it's not easy to see in the slide, but it's actually a routed circuitous wire there, which is a heater. And then at the top is actually a capacitor. And it's the capacitance which is used to measure humidity. But it needs to be kept at a certain temperature, and the temperature needs to be known very accurately to be able to determine humidity. It's quite a complex device. Most radiosonde manufacturers have to make their own of these temperature sensors, and this one is definitely Vaisala's secret sauce. And finally, the bottom of the radiosonde, we have an expansion header, which is quite convenient because the programming pins of the STM32 are broken out to it, which makes some things we're going to discuss later quite easy. In Melbourne, in fact, that connector is often found connected to an ozone sonde. There is a pretty much open protocol called Xdata, which allows other manufacturers of sensors. So we're talking ozone is one example, but there are many others, to plug their devices in to a radiosonde such as this one and have their sensor data relayed down to the ground via the radiosonde telemetry. Okay, moving on. I can cover this one. So how are they actually launched? As Michaela mentioned earlier, we use big weather balloons. These are made from natural latex. This picture is somewhat out of date because in this picture, the balloon is, well, what they refer to as natural latex color. Well, you know, it's roughly white. We don't have white balloons in Australia anymore. We have blue ones. This happened about 3 to 4 years ago and was a program started by the Bureau of Meteorology in the aim to stop wildlife from eating the landed balloons, in particular sea turtles, because white balloons in water look like jellyfish and turtles like to eat them. Blue, it seems that animals don't eat blue things, seems to be the general rule. I'm not entirely sure how true this is, but as a result, all the balloons that are launched nowadays by the Bureau of Meteorology are blue. They're filled with hydrogen, the explodey one. There are some places that still use helium. I think there's maybe 1 or 2 sites in Australia that do this, but it's not common anymore. And the target altitude range is somewhere between 20 to 30 kilometers, depending upon the launch. A typical, I'm going to call it a standard weather balloon launch, like what you get from Tullamarine Airport, goes to about 26 Ks. The more specialized flights like the ozone sondes will go higher, usually about 30 Ks, sometimes even more. Moving on. And what do we get out of these? So the typical data product of a radiosonde flight is called a skew T plot. And it's an incredibly overloaded plot, but meteorologists love this kind of thing. So anyway, the reason it's called a skew T plot is because the temperature aspect of this plot is skewed. In fact, it's angled on this plot. Now, and there's various reasons for this in terms of interpreting data. Now, if I quickly, actually, I'll just use this as an example. I'll just use what's on there as an example. Actually, sorry, no, I'll just share my screen to actually show you a live example from this morning. Right, here we go. So this is this morning's Radiosonde launch from Tullamarine Airport. It reached 29.5 kilometers, so a little bit higher than typical, and landed to the northeast of Melbourne. And on the right-hand side here is the data from this. Now, what we're seeing is it's a little bit hard to spot, so apologies for I can't make this any bigger, unfortunately. The red line is temperature. The blue line is dew point. So the point at which effectively air will condense. Now, and the vertical axis is pressure. So again, remember, we generally talk about pressure instead of altitude. Now, an interesting feature of these plots is we can immediately work out where clouds are going to form. So if the atmospheric temperature matches the dew point, condensation will occur. And that is essentially the altitude where clouds are going to form. I'm simplifying this drastically because honestly, I'm not a meteorologist myself, but right now from this one plot, I can see that there's probably going to be cloud at about 1,000 meters altitude or 3,000 feet, just from looking at this plot immediately. Now, the other thing that's shown here is the wind speed and direction. It's a little bit hard to spot here, but on the right-hand side, there's these wind barbs showing the direction and the wind speed. Each barb is 10 knots, if I remember correctly, of wind speed. I might be wrong on that one. But this one plot tells a meteorologist quite a lot about what is happening. All right, I'll stop sharing.
All right, so let's get that. So where are these weather balloons and radiosondes launched from? Basically, if you're anywhere in Australia, there will be a launch site near you. It might not be super near you, but the good thing about these things is because they fly in the air at quite some distance, if you wait long enough, you will have a balloon land somewhere near you at some point. So you just got to sometimes be patient. But yeah, in Melbourne, we sort of have two launch sites of primary interest. We've got Tullamarine Airport, so those get launched twice a day. There's sort of the usual radiosonde launches. The other one of interest is the bomb training annex. And there's two kinds of launches that happen from there. There's the ozone launches. They happen typically every Wednesday, but those are sort of a special thing. So sometimes over like holidays and that, you won't see an ozone sonde launch. But typically every Wednesday, sometimes it's on a different day. It's a bit erratic. But yeah, the other thing you might see from the training annex is if they're testing radiosondes, comparing radiosondes, or doing training. There's been days where they've launched something like 6 radiosondes in a row. So yeah, it can be quite fun chasing those ones. So yeah, there's radiosonde launch sites everywhere. Sometimes you just have to be patient if they're further away from you that balloon lands near. So a typical flight launched at 11:15 and 23:15 UTC time. Basically, they're trying to get a sample at sort of midnight and midday UTC. And the reason for this is they want all the samples like around the world to be the same time. So those are the times that have sort of been set. Usually takes about 1.5 hours, ascending at about 5 meters per second. Mark can probably update us on the exact average calculated value that we have for Melbourne, but typically they're around 5 meters a second. Burst at around 27K altitude. lands 30 minutes later. So you can see a sort of a plot of a radiosonde flight here to the right. And the radiosonde keeps transmitting for roughly 6 hours if it hasn't been damaged. It has an internal timer in it that will shut the transmitter off after about 6 hours of since burst. And that's so that when they launch the next balloon, there's not a transmitter that's interfering with them if it lands on a hill or something where their receiving station can hear it. So I'll pass back over to Mark to talk about Radiosonde Auto RX.
Yeah, so Radiosonde Auto RX came out of myself getting into radiosonde tracking. I reckon it was probably just after I got my amateur radio license back in 2011. And back in the day, Adelaide Airport was launching RS92 radiosondes, Vaisala RS42s. This is the previous generation. And unlike nowadays, where they essentially always use the same frequency over and over again, when they were using RS92s for various reasons, which I still don't quite understand, the transmit frequency of the launches would change every single launch. Sometimes only by 10, 20 kilohertz, sometimes by quite a lot. And it seemed to be completely random. As it turned out, the ground station software, which picked the frequency, was looking at the spectrum, 400 to 403, and picking the part with the lowest noise. Even though the license said they should be using 401.5. But anyway, that's the Bureau of Meteorology's problem. And so it became very difficult to try and know in advance what frequency a radiosonde was going to be on. So we were, every time a balloon was launched, we had to scan around and try and find it. So I thought, this is screaming for automation. So that's what I did. So what Radiosonde Auto RX does is we'll scan the entire radiosonde band. It will look for peaks and it will decode radiosondes automatically. It is a wrapper written in Python around what were existing radiosonde telemetry demodulators by another guy in Germany. Very, very smart fellow. And as of nowadays, it supports pretty much every common radiosonde type out there. There are a couple of Russian ones we don't currently have support for, and the Chinese ones, which we just have zero information on. But everywhere else around the world, everything's supported. It's targeted for a Raspberry Pi, which started out in the Raspberry Pi 2. It should still work on a Raspberry Pi 2, but who has those anymore? And there are currently, and this number really scares me, there's 660 receive stations running this software. My software, I hope it works. And it uses software-defined radio. So yeah, the aim was to track all of the radiosondes. So next slide, please. And we're doing this using software-defined radio, in particular, the RTL SDRs. I'm sure many of you will have heard of these. Many of you might even own one of various forms. With these, we can capture a chunk of RF spectrum up to 2.4 megahertz, and then do the rest of it in software. Software-defined radio, as the name suggests, is software-defined, a radio that can be used for many purposes. You can get them for extremely cheap. I would avoid the really, really cheap ones. If you're paying about $30, you're probably getting about what you're asking for. And I recommend the rtlsdr.com ones, which cover a pretty wide range, 20 megahertz. Actually, they can go lower with direct sampling to 1.7-ish gigahertz. Perfect for our application. So in terms of antennas, well, you don't actually need very much. It's worth remembering that radiosondes, for the most part, they're in the air. So we have what is essentially a perfect line of sight path. So it's free space path loss. And a quarter wave mag mount, or quarter wave monopole, I should say, is sufficient in almost any cases and is often the optimal antenna to use. And if you think about it, that's because there is a good possibility a radiosonde might fly above you. So if you have an antenna with too much gain, you may find that the radiosonde ends up in an antenna null above you, or possibly even at a lower elevation, depending upon how high gain your antenna is. So high gain, not always the best solution for radiosonde reception. For mobile use, which we'll talk about some mobile tracking a little bit later on, mag mount antennas are fine. You can actually pick up a The one that's on the bottom right-hand corner of the screen there is from AliExpress for $2, and it works just fine for this job. If you are tracking signals that are perhaps quite a bit further away, sometimes a preamplifier can be handy, but I should say for the most part, a regular RTL SDR is going to be perfectly sufficient. Next slide. So what are we doing in software-defined radio? Well, in this case, it's turning RF into telemetry. So at the top of the screen, we have on its side waterfall graph. If you're used to a waterfall plot or a spectrogram which flows down your screen, this is the same thing on its side, showing a signal from an RS41, which is sending frequency shift keying telemetry at 4,800 bits per second. We decode that telemetry, and after a lot of reverse engineering and a lot of work, we extract the relevant data which we care about, which is the time, position, and temperature information as well, along with the serial number. So what is happening exactly in Radiosonde Auto RX overall? Oh, some formatting issues there. Anyway, so first up, we have the RTL SDR at the front with our antenna. That's converting our RF signals to samples, which we then process. Then moving along, I need to try and find our radiosonde. So what we do is we use a utility called RTL Power to produce a spectrum, or basically a power density spectrum, which provides us with the power versus frequency over the radiosonde band. We do a peak search and look for peaks in that spectrum. For each of those peaks, we go and use the sonde detector algorithm, which looks for particular headers. So as it turns out, each radiosonde out there uses telemetry which is different enough that we can distinguish it based upon the header of the telemetry alone. And that tells us, first off, is it a radiosonde? And secondly, what kind of radiosonde is it? So now we have found a peak, we've detected the fact that it is a radiosonde, and now we can start up the radiosonde decoder itself, which starts producing telemetry. And this can be uploaded to various sources, like the Sonderhub tracker, which we'll talk about in just a moment, and also local mapping, a system called Chase Mapper. So next slide. This is the web interface. It's actually a little bit dated, but it's still reasonably accurate, of Radiosonde Auto RX. This is something you access on a web browser. It's running on your Raspberry Pi, but you might access it somewhere else on your home network, and you can see exactly what it's doing. So there's a map in the center showing the location of a radiosonde. At the bottom is the output of that spectrum scan, where we can see some signals have been detected. In fact, only one of these is a radiosonde, but because we are looking for that header information, we can discard the other signal, which might just be a birdie or some other interference. There is actually a surprisingly large amount of activity that's not radiosondes in this frequency range. It is also used for commercial satellite operations, including one that I'm currently working on. If we go to the next slide, we can see at the top, there is the live telemetry as we're receiving, so showing positional information and the information on temperature, and nowadays we have humidity there as well. And finally, we have where the radiosonde is and where you are as well on the map. Over to you.
All right, so before we jump into Sondehub itself, I wanted to sort of give a brief history of how the heck did we get here. So yeah, Mark created the Radiosonde Auto RX project, and that originally used Hub, which is an amateur radio weather balloon tracking website, similar to Sondehub, but it tracks amateur balloon launches. Very, very useful. When I started tracking, there was only a handful of stations in South Australia, plus my lonely station in Melbourne, and all was good in the world. So eventually more and more people started tracking radiosondes this way. Hub got a little bit annoyed with seeing so many non-amateur balloon launches on their website. So they filtered out by default all the normal weather radiosondes. So Sondehub.org was purchased, and it was set up as just basically a redirect to HabHub with the filter removed, so you could see all the radiosondes. And this was great until there were so many people tracking radiosondes that it became 99 or probably closer to 99.99% of the workload on HabHub. And HabHub started to slow down, and it was kind of all our faults. So the idea was that we'd move off HabHub and we'd create our own backend. And that's sort of where Sondehub is today. We run all of our stuff ourselves. We don't rely on HabHub at all for any infrastructure. And it gives us some unique features. So because we wanted to reduce the load on HabHub, we originally limited uploads to 30 seconds. Now, most radiosondes will essentially ping out information every 1 second, but we didn't want that in HabHub, slowing it down. But in Sondehub, we don't have that limitation, so we collect all the data. We have all the data you could ever want from a radiosonde being tracked. Yeah, so the other thing to sort of note about Sondehub is it's not like software specific, so it's not specific to Radiosonde Auto RX. There's actually some other software out there called, I think it's RDZTT Go, which is a embedded radiosonde tracker, and that feeds into Sondehub as well. So it's designed to be a generic platform. So if I jump into the next slide, basically project goals, public repo for radiosonde data from crowdsourced receivers. We want live open data of radiosondes. So one of the unique things that we have with our data is we distribute it live. So you can see the data straight away. You don't have to wait for a global weather forecast model to be generated. You can get it as the radiosonde is going up. So quite unique. You can access that data straight away, which is really cool. We want it to be able to interface with other apps. So, you know, we're in the unique position of collecting this data. We want to be able to share that with basically anyone who wants to build something cool. Backend's receiver agnostic, as I mentioned, and we want this to be scalable. So, you know, we've had occasions where like the weather people in the US have done live streams on Facebook, and we want our website not to crash when that happens. So yeah, we try and work hard to make it reliable and scalable. So basically we log about 300 unique radiosondes a day. We have about 660 receiving stations. That number goes up and down, but generally it's tracking up, which makes my life difficult because I have to keep on building more and more infrastructure. And we process about 7 million radiosonde data frames every single day. So quite a lot of data. As we mentioned earlier, radiosondes have sort of this typical schedule of, you know, twice a day. You do get some other radiosondes launched between those points as well. So we end up with this distribution of, you know, a fairly heavy workload at 2 points in the day and a couple of other points. So yeah, very, very cool. So I'm going to jump in and show you Sondehub. So let me flick over here. So I've got the Melbourne radiosonde up here at the moment. And hopefully this is zoomed in enough.
Looks fine.
Looks fine. Cool. You can see it all. Excellent. So we can see a little bit here on the left-hand side. We've got a list of all the radiosondes. I've got this set to 12 hours at the moment, so it's a big, long list. But we can see ours in the left-hand side. Over the left-hand side, we get some critical data, such as, you know, what's the current altitude, the battery voltage, the frequency, radiosonde type. From here, we can open up the SKU-T chart that Mark was talking about. Let's get rid of that for the moment, though. We've got a telemetry graph. So with RS41s, we're able to decode pretty much all the information that's sent back on them, which is really cool. We get to see the humidity, the satellites that it can see, the battery voltage, the temperature. And basically, if you drag this plot along, you'll see at what, like, the location that data was received in. So you also see this little line here. This is showing that this packet was received by the station, Big Ears. This is a really good station in Melbourne for the folks that run that. It does a great job of tracking radiosondes. But you can see all the different stations here, the green dots and the bronze dots. Basically, the bronze dots, silver and gold dots are Patreon supporters. This infrastructure isn't free. It costs money to host. So we're very thankful for our Patreon supporters that help us with that. You'll also see down here, these are recovered radiosondes. So these are ones that have been recovered by people.
Let me guess, VK3PF. Really,
yes.
That didn't actually show up, by the way.
I know, I don't know. I think this is a Safari bug. Future things to fix. So yeah, let's have a look at, let's see if there's a radiosonde. There will be a radiosonde somewhere in the world. So yeah, we can have a look at a live flight. We're getting data in. We can see the receiving station track. The other thing that we can see here is we start to get a prediction of where the radiosonde might possibly land. And so you can use this to help with your chasing. So I believe Mark's going to show us Chase Mapper in a bit, which is a better way of chasing radiosondes. But this little prediction is quite useful if you're just starting with radiosonde tracking and want to try and find one without setting up too much of your own software. But yeah, so we can see the previous track, the prediction, the landing spot. The other thing that we'll see, which might be hard to see because this is a yellow one, I don't see it there, but we also do reverse predictions, which try and work out where a radiosonde was launched. So an extra little fun bit. But yeah, we can see the recoveries in here. You can mark a radiosonde as recovered in here, which is handy. And there's a whole bunch of settings and tweaks and stuff that you can explore. So yeah, let me jump back to the slides. So let's have a look at chasing a radiosonde. So ideally you want an RTL SDR and an antenna. And the reason sort of why this is important is you want to be able to get the landing position of the radiosonde. All the other stations might not see the landing position of the radiosonde. So you want to be very close to the radiosonde where it lands. So that's why we want to run that stuff locally. So you want a laptop or a Raspberry Pi running Radiosonde Auto RX and Chase Mapper, ideally Chase Mapper. It's not strictly required, but it helps a lot. And something to view Sondehub and Chase Mapper on. So if you're if you're setting up a Pi, you want to be able to see the stuff on the Pi, and optionally a Yagi antenna, and we'll get into why in a sec. So Mark is going to tell us a little bit about this setup.
So this is a literal screenshot of Chase Mapper. Now, some of you who were involved in a barbecue event, I think it was last weekend, possibly it was a weekend before, may be familiar with this, because this is the same software which many of your members over at EMDRC might be looking at using to chase your own balloon launch. It was originally written for chasing radiosondes, though. Well, partially anyway. And this is a web browser-based application. It runs on a Raspberry Pi or a laptop alongside Auto RX and displays the balloon position and where you are as well, just like what the Sondehub map does. However, this was written to work offline, and that was mainly because we do, I've been doing balloon launches out of Adelaide for a very, very long time. I think I gave a talk on Project Chorus a few months ago, and we quite often go out of phone coverage range. So relying on an online mapping system is usually a bad idea. And so this system was written as a way of being able to not rely on the web. So it can download map tiles, so I can use them offline. It can download portions of the weather models that are used to run these predictions and use those offline. And effectively it'll guide you to the landing spot. It shows where you are, where the payload is, where the predicted landing spots are. Your aim effectively is to follow the prediction dot. And if everything goes well, you will be in place to, at the very least, get a landing position, and at the very best, watch it land in front of you, depending upon where it lands, of course. So this software is open source. It is freely available. And I believe locally, some of the Raspberry Pi Hackers guys have made a Raspberry Pi image with this preloaded. I think it's configured to run the amateur balloon tracking software, but running Radiosonde Auto RX alongside it isn't that hard either. So yes, this is probably the best way of getting to a radiosonde landing site reliably and quickly. And in Melbourne, that matters because unfortunately in Melbourne, there is significant competition to recover these things. Unlike many years ago, there are now many people out hunting these radiosondes for fun.
Yeah, I used to, when I first started chasing the radiosondes, it was just me. I did not see anyone for like a year or so. So yeah, it's fierce competition now. So the other thing mentioned on one of the previous slides was a Yagi antenna. This is kind of optional. The new Radiosondes RS41s give pretty good position reports. But sometimes, like especially if it lands in the middle of a field or forest or something like that, and you really want to get it, it's useful to have a Yagi antenna that you can wave around, measure the signal strength, and basically fox hunt to the radiosonde. I found this particularly useful in a field. Basically, I could not see the radiosonde until I stood on it. So without the Yagi antenna, I would not have been able to find that. It doesn't have to be a fancy Yagi antenna. So on the slide here, I've got a just one of those tape measure Yagi antenna designs that you can find online, and this has worked really well. And because it's made out of tape measure, you can bash it around and it does not matter. So yeah, that's good fun. And Mark is going to show us about predictions on Sondehub.
Yes, I am. Once I sort out my screen sharing again. Sorry. So back on Sondehub, of course, and I'm showing the Melbourne sonde again. But so one of the big things about chasing, and this applies for radiosondes as much as your own balloon launches, as well as you really want to have some understanding of where they're going to fly before you either launch a balloon or decide to go for a drive to chase a radiosonde. Thankfully, that weather model we talked about earlier helps us out with this. It is a predictive weather model. It predicts up to about a week ahead, though the prediction quality falls away drastically after about 3 or 4 days. And on Sondehub, we've built in the ability to run these predictions. So if I go to a launch site, I'll pick Tullamarine. If I click on that, this little pop-up window shows us what we know about that launch site. So we know that it launches RS41 radiosondes. We know the nominal frequency. We also know the launch schedule. So it says it launches every day at 12 UTC. And I should note this is the nominal time. It actually launches at 11:15 and at 0 UTC or 23:15. And we can click this Generate Predictions button. And what that will do is, using that Global Forecast Systems model, it will go and run predictions for every balloon launch time as far as the model will allow. And I'm just waiting here because this can take a little bit of time sometimes. Here we go. And getting there. All right, here we are. So these red lines show their predicted flight paths. And each of these lines ends in a little marker, starting at 1, 2, 3, 4, 5, 6, 7, etc. 1 is the next launch, which in this case is, well, the next landing time, which is forecast for 10:45 p.m. That's my local time in Adelaide, apologies. And then 2, which is tomorrow morning, 3 tomorrow evening, 4 the following morning, etc., etc. And so this gives you an idea of what's going to be happening over the next week. So to me, Number 4, that's interesting. That's the 3rd of July, which is that Sunday? I think that's Sunday morning. Yeah, that is Sunday morning. That's landing in suburbia. That one will be chased. I can guarantee you there will be probably at least 3 or 4 people out going after that particular balloon launch, trying to recover that radiosonde.
After this talk, Mark, after this talk, I expect every EMDRC member to meet up at that point.
Oh no, this is Sunday night, not tonight. Tonight's up here in the middle of the King Lake National Parks. That might be slightly harder to recover, but Sunday morning, interesting radiosonde to watch. So just an example showing these predictions. So this is very important if you're going to go hunting your own radiosonde, because you're probably not going to want to go hunting if it was going to land somewhere out here. And unfortunately, this is a fact of life with Melbourne. Either lands in forest, or it lands in forest, or it lands in water reserve, or it lands a long way away. And then very occasionally it lands in the Melbourne area.
All right, so let's go with my or your first radiosonde, sort of how to get started. And this is the sort of the bare minimum, like very basic setup. You can get very elaborate, setting up chase mapper and all of that, but let's start very, very simple. So step 1, wait for a good prediction. So use the predictor that Mark showed you on sonderhub.org to find a prediction where 1, you have time off and you're not, in the middle of work, and 2, somewhere sort of close by, or if you want to go for a long drive, it's always a good excuse. Second step, run Auto RX in your laptop, on a Pi or laptop, whatever. Watch sondehub.org to see predictions. If you're not running Chase Mapper, you can just use, provided you've got phone reception, you should be able to use sondehub.org to see the predictions. Drive to roughly the landing zone. The prediction's going to move, so just keep that in mind. If the prediction is wildly out, just wait a few minutes for the next prediction, so you can gain some confidence in the predicted landing zone. Hopefully the radiosonde will be laying in the middle of the road or in the middle of a farm. The next step is to take a photo of the radiosonde. This is a very important step, because you should celebrate that you found your first radiosonde. And finally, you need to tweet bomb for, well, I guess for EMDRC peeps, it's going to be @bombvic. And you put the hashtag as the serial number of the radiosonde. We love doing this, and it's great to look back at your old tweets for all your old recoveries. So very fun to do. So where do radiosondes land? Well, they can just land in the middle of a paddock. They can be quite hard to see, but there's one all the way out there. That was a little bit of a walk to get out there. And this is after we've walked, I don't know, a K through a field to start with. They can land in like rocky terrain. You'll see bottom right-hand corner is the radar reflector I was talking about. That's on Australian radiosondes. And in suburbia, so very often on the top of roofs or in the middle of the road. The great thing is the string between the radiosonde and the balloon is quite long. So typically one of those will land somewhere where you can reach, and you can just pull the other side to get the entire thing back. Squid poles, very common in amateur radio, also very handy for recovering radiosondes that are stuck in trees. But yeah, so what do you do with these radiosondes once you've got them? So there's a few recycling options. Radar reflectors are shiny. They're great fun. You've got string and rope, can tie stuff up. You've got batteries, the TV remotes. These are batteries that have gone to the...
I should note that every radiosonde comes with 2 free energizer lithium AA's, only partly used. Yes. The quicker you get there, the less used they are.
And, they've gone to near space, not quite space, but, getting there. And you get a STM32F103, which is like, super, super handy to have. So yeah, with the radar reflectors, you can make little Christmas trees like that. You can decorate your Christmas trees with the radiosondes. All good fun. Ozone sondes. So we briefly touched on this at the start of the talk. Melbourne is very, very lucky. And I'm guessing probably very competitive now. This used to be an easy task for me. I haven't done it for a while, so I'm going to guess there's probably a lot more chasers now. But the ozone sondes have a $50 reward. Just remember, if you're trying to do this for money, make sure you factor in your fuel price, because you don't want to go chasing these forever in the hopes of the reward and only spend it in fuel. But if you return these to BOM, they will reward you with a $50 check, and they pay for postage. So good fun.
They'll also send you a lovely plot showing the ozone sounding data as well.
Yes. So I'm going to throw to Mark, who's going to talk about flashing the RS41.
Right. So as I mentioned before, at the bottom of the RS41 is this lovely little programming connector, well, expansion header, which just happens to have the programming pins broken out onto it. There has been a fair amount of work done to write various bits of software for this hardware platform. As was the title of a previous talk that we did, these are STM32 development boards that literally fall from the sky. And there's quite a lot you can do with them. Unfortunately, the actual temperature and humidity sensor circuitry is quite complicated, and no one's actually written code to reuse that. However, the GPS receiver, the microcontroller, and the radio work perfectly well. And there's a range of open source firmware. I've got some examples here. The one at the top is what we recommend for use if you're going to use one of these on your own balloon launches, as a very, very reliable flight tested balloon tracker. This particular one, RS41NG, does a number of different modes, including the Horus binary telemetry mode that I developed a few years ago as a very robust tracking system. Many of you may have already set up to receive this, and for, I believe, your launch is coming up, you'll be using one of these RS41s to track the flight. They also make a really nice fox hunting beacon on 70 centimeters anyway, and there's a repository there, RS41 Fox, which makes it act as a fox hunting beacon, and we use these in our regular fox hunts around Adelaide. I've got a couple of RS41s painted black with magnets in them. And we just turn them on, slap them to a magnet, slap them to a street sign or whatever, and off we go. The radio is only really usable for 400 megahertz. In terms of reflying them, as I've spoken previously, we use these in Project Horus for our own balloon flights. Project Horus, we've done 60 launches or so since 2010. And we used to build our own, well, for our primary tracking, telemetry, which has to work. We built our own trackers. Nowadays, it's all RS41s because they work, they're reliable, they're plentiful. I keep on getting given bags of them for some reason. So, it's great. And yeah, they just work beautifully, and they're quite light. It's only about 80 grams for a RS41 tracker. And yeah, using this custom Horus binary mode, which we use nowadays. And that, by the way, that was co-developed with David Rowe, who you may know from Codec 2 and FreeDV. Okay, moving on.
Cool. So basically the other things you can do with them is any STM32 project that can fit in 64K. Have you, I'm not sure if you've looked at how to get STM32s at the moment, but basically everywhere is out of stock. But these things are falling from the sky. So if you have a STM32 project and you're waiting for the chips themselves, just go Radiosonde hunting for a bit and you'll be right. But apart from that, you got a very expensive, free wireless thermometer if you use the standard built-in RS41 firmware. But I mean, like, these things could be repurposed for smart home 43 433 megahertz devices, or, you can use the GPS on them. In fact, I've cut one of the RS41s up and just used the U-Blocks chip as a GPS for a Raspberry Pi at one stage. Quite cool. So next up, I want to show Sonderhub Amateur, and this is a very new thing. So I haven't actually shown this to many people yet. So this is exciting. So let me jump over to that. So this is Sonderhub Amateur, and you'll notice that it looks very much like Sondehub. Basically, the entire backend for Sonderhub Amateur is shared with Sondehub. So it's got the same reliability, the same scalability, and being that it's being used for amateur stuff compared to radiosondes, we're not going to overload it with amateur data. So,
well, you said that until last weekend when I broke things.
But we still captured all the data, which is the important thing. So yeah, it's super reliable, and when it breaks in a fairly safe way that we can still capture all the data out of it, which is cool. Now, there was an active flight on, but we've talked for too long, and the last packet I've got here is 32 minutes ago, which is unfortunate. But basically, it's the same as Sondehub, but you'll notice on the left-hand side that we have amateur radio balloon flights. Now, at the moment, we accept data in a few different formats, which I think I have a slide for in a sec. But basically, it's more or less Sondehub, but you'll notice that we've got the different trackers in here. They're not Radiosonde Auto RX, they're Horus GUI, and we also have APRS flights in here, which is pretty cool.
It's worth pointing out, let's scroll down to Australia again. You will notice VK3ZWI-18. That is a Pico balloon launch from some school that I forget. That is the Victorian WIA call sign, by the way, which they're using. And that's been around the world twice so far. So this is a Pico balloon flight underneath a foil party balloon, I believe.
Nice. And I think this one uses Whisper and probably comes in via APRS. And yeah, so we can see that there's already receivers in Victoria running Horus demod.
One of those is on the Zoom call as well, VK3BKQ. Hello.
Nice. So other things in here is that we get we can configure predictions. I'm not logged in here, unfortunately, so you can't see that.
It's on a slide. It's a couple slides away. So
cool. We'll have a look at that. But yeah, it's more or less the same as Sondehub. It's just amateur version, which is really cool. So let me jump back to slides. So yeah, like we said, we have a REST API, so anyone can upload data to this. We already have Horus GUI and demodlib doing that. So if you've got new versions of those will support Sondehub. Various Whisper gateways are starting to support Sondehub. The Sondehub Python library. The Things network is work in progress. Various other people are starting to experiment with this as well. We also capture data out of APRS. We don't prefer people use APRS if they want to get data specifically into Sondehub. It's just we're capturing it because we want to capture that data and try and get as much data as we possibly can. And we get some Whisper balloons as a side product of that via APRS IS. So yeah, in Horus GUI, there's a little tick box. You might have seen it already. There's the habitat upload and there's the Sonderhub ham upload. So custom predictions. If you're doing a amateur balloon launch, you might have a different peak altitude that you're expecting, a different descent rate. You can set that all up in Sonderhub Amateur, and that way the predictions will work correctly for your flight, which is cool. We also support floating flights. That's where a balloon goes up to a certain altitude and sort of floats at that altitude. So we capture all this data. We can create dashboards for it in our Elasticsearch cluster that's publicly accessible. People can sign up for accounts for that and start querying the data, which is neat. Mark wanted me to specifically point out this specific data where you can see the battery voltage versus the temperature, and you can see as the temperature of the radiosonde. I believe this was an It's Windy. As you can see, there's no more data after that point. So yeah, in terms of Sondehub, Radiosonde receiving, all of that sort of stuff, how do you get started? Set up a receiving station with Auto RX. Chase your first radiosonde. It's not that hard to do. It's lots of fun. I know you love fox hunting. My view is it's government-funded fox hunting twice a day. The only difference is that the foxes tell you where they are, so that makes it a little bit easier. Help out with tracking amateur launches. You know, some of the launches from the SA, the VK5s end up over the border, so it's fun to track those as well. And build a radar reflector sculpture. You know, once you collect a handful of radiosondes, you end up with a stash of radar reflectors and build something cool out of that. So I just wanted to quickly jump into something else that's somewhat unplanned. This is like brand new, sort of while we're working on the slides. We've got Grafana, which is a data analytics platform, and so we've set this up to make getting data from the amateur side of things a little bit easier. Now, this could explode while I'm demoing it because we haven't had much time to play with it. But say I want to have a look at this up and up.
Yeah, that's a good flight. The up and up flight's a good example.
Hopefully, I should be able to click on here, go open up and up, and it should fetch the data. Hope my LTE works. Yeah, look at that. And I'll just select this time window a little bit here, and we get the altitude. We can actually see this is like a heat map of the frequencies reported. So for some, because of the temperature changes, you'll sometimes see a different frequency over time. So that's plotted there so we can see what's happening. We've got different packet counts from all the different receivers. We've got a map, although we need to zoom in on it. Let's quickly do that. We've got a map of the flight. We got the velocity that's changed, the SNR of all the different receiving stations. So if we want to have a look at how VK5 AREG does over time, we can see that. The satellites, all the fun telemetry stuff that you want. The pie chart that everyone loves, and Mark has been bugging me, is so much to get, along with most importantly, being able to easily access the data.
Here in South Australia, it's so competitive, the pie chart. So people want to get as many telemetry packets as possible. There's been threats of people putting pins in people's coax to make sure they end up higher up the list on the pie chart. Everyone loves their telemetry.
Yep. Yeah, so this is something new. We're still working on it and expanding on it. But basically, we'll want to make it easier for amateur balloon launching people and data collectors to be able to access the data about their flights as quickly as possible. This update's live. I haven't seen a live flight on this yet because I'm currently on holidays and I haven't had a chance to look at it, but it would be interesting to see. So with that said, I'll jump back to slides for our sort of final slide, which is if you're looking for Radiosonde Auto RX to get started, there's the GitHub link there. If you want to have a look at the Sonderhub website itself, sonderhub.org. If you want to look at the amateur Sonderhub, it's just amateur.sonderhub.org. And yeah, our contact details there again if you want to get in touch. And I'm not sure if Mark had anything else to add.
That's all. Thanks everyone for listening.
Yeah, thanks.
And hand it back to whoever's hosting to take questions.
It's me. Hello. Thank you so much for that. That was a really interesting talk. let me go and get on video if I can. Hello, everybody. Yeah, once again, thank you for that great presentation. I'm sure Michaela and Mark are happy to take any questions. Anybody got any questions? Anybody on Zoom? Sorry? Do radiosondes float on water or in the sky? Oh, on water.
Yes, they do.
Yes, both to those.
So yes, they're foam. The cases of foam, they will float on water. They will take on water, and eventually they will fail and make sad sounding noises on the telemetry as it happens. Floating in air, we have seen actual radiosonde launches float before as well, right across Europe, producing huge amounts of traffic and annoying Michaela to no end because it produces huge amounts of data ending up in our database. Doesn't happen very often, thankfully.
Yeah.
I think you might want to explain how that happens and what floating.
Sure. So floating balloons are very much a thing. Essentially, what happens is there's usually less. Effectively, the balloon doesn't burst before it reaches equilibrium with the surrounding atmospheric pressure before it bursts. This can happen from underinflation, sometimes from a leak around the balloon neck where gas can be released during ascent and then reclose again as gas is let out. And eventually, basically, can let out enough gas that the balloon will just float at a certain altitude. Now, thankfully, meteorological balloon flights will not float for very long because the latex balloons they use will break down under UV. Usually you get at worst a day out of them before the balloon actually breaks down enough to be damaged and eventually burst.
Great, thank you. Okay, anything else? Anything in the chat? No, nothing in the chat.
Yes, question from John about Pico balloons. So, okay, so Pico balloons they've gained in popularity over the last few years, mainly because they're a helicopter. Well, I'm not going to say they're a huge amount cheaper to do than a full, I'm going to call it a full-size balloon launch. But many countries have regulations which allow you to launch balloons under a certain size, generally without requiring any approvals. This is the case in many places in Europe, in the US. Depends who you talk to in Australia. Their legislation says that it's okay, but if you go talk to CASA about it, they will say no, depending on who you talk to. We're talking about, by Pico, we're talking about payloads that are usually 10 grams or less. They're very, very lightweight, and they're launched under often effectively roughly 36-inch diameter party balloons. But these are particular balloons which are designed to not burst. They're called super pressure balloons. Well, that's the style of them, where the pressure in them increases to a certain point. They're strong enough that they don't burst, and eventually they will start to float. So in the case of the VK3ZWI launch, I'm not entirely sure. I don't have the details on exactly who did that or what exactly they used. But that's lasted long enough to float around the world twice. This has been going on for many years now. The first circumnavigation by a Pico balloon was back in about 2013, I believe, by a guy from the UK. Pico ballooning, yes, as I said, it requires extremely light payloads. That used to be a case if you had to go build your own, which was a significant challenge. Now you can buy them off the shelf. So QRP Labs sells a tracker, which is about 5 grams. And these flights normally use whisper telemetry. So because they're floating around the world, they will be well and truly out of range of, line of sight. So UHF and APRS generally won't work. So they use HF instead. And They're usually flying vertical dipoles for 20 meters or 30 meters, normally 20 meters, and are transmitting whisper, but not as you know it. It's whisper telemetry with various other bits of data included in telemetry fields to provide positional information at more resolution than what whisper normally allows, and provide altitude information as well. That's picked up by the Whisper network, whispernet.org, and then people collect data out of that system and push it into either our mapping system, Sonderhub Amateur, or APRS, and hence we get it from there as well. So that's a short version of Pico ballooning, best that I can do. So a Pico balloon flight might only cost, depending upon the tracker cost, it doesn't require much helium to launch these. However, getting it right, getting it to the point where it actually does float is a significant learning curve, and often you lose a lot of trackers along the way before you get it right. It's very difficult to get it right the first time.
What's the weight of the bomb payload, the RS41?
80 grams. Though it is possible with modification to bring them down to 35 grams by stripping off a lot of basically everything except for the PCB and removing and bringing it down to one AA battery. You can get it down to 35 grams. That still is not light enough to fly around the world, and the battery wouldn't last long enough anyway.
All right. Any other questions? Not hearing anything. So once again, thank you both very much, especially Michaela from Queensland. And yeah, because this whole thing got a little bit rushed with the internet issues, I don't have our nice EMDRC banner or flag that we usually present to our speakers. So you'll just have to come around on one of our open days and collect it. And that concludes the official part of the evening. So everybody can now chat amongst yourselves, and those here can enjoy coffee and biscuits.